All right, so we are going to look at the past questions, which is 2021. Now, the first question here says, outline the chemical synthesis of diethylstilbestrol using p-methoxybenzaldehyde as starting material. Now, we've answered this question before, right? So we don't, stilbestrol is still something as diethylstilbestrol. Now, discuss why steroidal drug modification is important to the pharmaceutical chemist using structural example to illustrate. We've done something like this before. Maybe you can just draw any of the structure like that of testosterone and that of what? Methyl testosterone, the differences, right? Now, discuss SARO of adrenocorticoids. Now, I told you that before you can discuss the SARO of any group of compound, you must first of all draw the structure of those compounds. Is that okay? Now, for the adrenocorticoid, your structure something like this. Let's draw the structure of the adrenocorticoid. Of course, you have your normal benzene ring, all right? Then you have another benzene ring, which makes it two benzene ring now. Then you have another benzene ring. You getting it? Which makes it three benzene ring now. And then lastly, you have this ring here. Of course. Good. So this is the structure you have. Now, for the adrenocorticoids, what you normally do is every other thing still remains like those of the testosterone and co. But what you normally do is there will be a double bond here. Is that okay? Because normally there's a double bond there for testosterone. So they're almost the same thing as the testosterones and the progestins. But one thing you should take note is for this one, every other thing remains the same like all the ones we'll be drawing since. But there's a substituent at this position here. Are you getting it? And then another thing is you have an ketor as opposed to the aldehyde group that is usually here. I mean the ketonic group that is here for progesterone, and the alcohol group for the testosterone. What you have here is CH2OH and then CO. This group here is what we call the ketor. Is that okay? It's called the ketor. If you want to bring it out, it's like something like the CH2. You have something like C double bond O CH2OH. You call it a ketor. Is that okay? Now, how do you number these compounds? First of all, before we start doing any other thing, our numbering system still remains the same. Is that okay? The numbering system still remains the same. So here is 1, here is 2, here is 3, here is 4, here is 5, here is 6, here is 7, here is 8, here is 9, here is 10, here is what? 11, here is 12, here is 13, here is 14, here is 15, here is 16, here is 17. Look at the normal structure. Now you agree with me that things that we need to modify are this O group here, this double bond here, these groups here also that we added, we need to modify them, and probably this large group here. So that will form the basis of our structural activity relationship. Now, fluorination in the 9 alpha position enhance. Now, there's also this position here. A substituent can also come here, like fluorine. So if you add fluorine to this position, it enhances the glucocorticoid action, but most especially it enhances the what? Mineralocorticoid action. Is that okay? So fluorination in the 19 alpha position enhances glucocorticoid and particularly mineralocorticosteroid activity. Is that okay? So if you fluorinate position number 9, so our target here in this case we should also be targeting number 9. Like you have fluorohydrocortisone is one compound. Fluorohydrocortisone. Is that fine? Now, you could also have this group here. You name it as arrow 1. And then you have this group here that emanates from here. This is arrow 2. Now, the substituent that you substitute into arrow 1 and arrow 2 will tell you the kind of glucocorticoid or the type of adrenocorticoid that you are actually looking out for. Is that okay? If arrow 1, what you have in arrow 1 is double bond O, and then what you have in arrow 2 is OH, you call it cortisone. While if what is in arrow 1 is OH, and what is in this arrow 2 is also what? OH, you call it what? Hydrocortisone. Then if you have fluorine at this position, then OH, you call it fluorohydrocortisone. Are you getting it now? This is just how they modified them and then gave different different structures. So that is that. Now, we say fluorination in the 9-alpha position enhances glucose and particularly mineralocorticosteroid activity. 6-alpha methyl compounds show increased glycogenic activity with no increase in mineralocorticoid activity. Now, this one, if you look at this structure very well, we are adding new things to different positions. At position number 6, if you have a methyl group here, what we are saying is that it increases the glucocorticoid activity, but does not have any influence on the mineralocorticoid activity. So that is that. Now, all these other ones, they are stories. Just know at least some. Dehydration to give a delta 1 compound leads to an increase in the glucocorticoid while reducing the mineralocorticoid activity. Now, what do we mean by that? If you have a situation where this double bond move to this position number 1, are you getting it? It gives high what? Glucocorticoid activity as compared to what? Mineralocorticoid. This delta 1 means the bond is at position number what? Double bond is at position number 1. Is that okay? Example is prednisolone. Now, if you check your note for the structure of prednisolone, you agree with me that prednisolone rather has a double bond at this position here. Are you getting it? Then it has another double bond here. So when there's a double bond at this position here, it increases the glucocorticoid activity, and also it increases particularly the glucocorticoid activity and reduces the what? Mineralocorticoid activity. Is that okay? So prednisolone is more of a glucocorticoid than a mineralocorticoid. Is that okay? Now, that is one. Now, even prednisone also, prednisolone, prednisone, they fall into the same category. Now, dehydration of the 9-fluoro compound increases mineralo and more particularly the glucocorticoid activity. That one is still, we are still saying the same thing. The 6-alpha fluoro substituent also significantly increases anti-inflammatory and glucocorticoid activity. 6-alpha. It means at position number 6, if it is the fluorine substituent you have here, at position number 6, what it does is it increases anti-inflammatory and glucocorticoid activity. A double bond between position 1 and 2 increases glucocorticoid activity without increasing what? Mineralocorticoid activity. Example of that is, what compound do you think has the double bond at position number 1 and 2? Is there any compound apart from prednisolone? Is there any free compound that just have it at position number 1 and 2? Most especially prednisolone. That's the only compound we have here. Alright? So that is basically that for this first one here. You just have to memorize all these things. There's no two ways about them. Now, outline the synthesis of norethylsterone using O-methyl ethylsterone. Now, the first thing you need to do is what are the structures of non-ethisterone and O-methyl ethisterone? That's the first thing you need to actually know how to draw. What are the structure of non-ethisterone? Non-ethisterone is like ethisterone that you remove at position number 19, remove CH3, right? So you are going to have ethisterone is a pregnane. So, but we remove it is a pregnane, but we remove that OH group. Okay, let me just write it instead of trying to draw something like this. Let's draw the structure of ethisterone. Non-ethisterone rather. Have double bond O, this group here, and then of course, and then you have something like this. At position number 19, you don't have any double bond, so it means you will not be having any bond here at this position here. Then for ethisterone, according to what we said earlier, you are going to have C triple bond CH, right? And then at this position, what are you going to have? OH. We want to synthesize this compound, which is non-ethisterone. We want to get it from O-methyl estrone. Now, there's an important property of the estrone that you must take note of. It may come out as an objective question, and they may also, the estrone, they have a phenolic ring as number 1, as ring A rather. They have a phenolic ring as ring A. They are the only one that have phenolic ring. The estrone, estrogens. Are you getting it? They have phenolic ring. When I mean phenolic ring, means they have this, all the bond what? Doubly bonded. It's a question that you may come across. Then ring 2 is still the same. You have O-methyl estrone. And then you have something like this. Alright? O-methyl estrone. Now we want to actually draw estrone. We definitely have go east. That's 18 carbon. So what we are going to have, we are going to have one bond here at this position. One CH3 attached here. Is that okay? And I know here may either be a double bond oxygen O, or it may be, yeah, here may be a double bond oxygen O, or it can be OH, any one of them. Double bond O. Now, however, they gave you O-methyl estrone. Now, what does that mean? It means at this position here, you have a methyl group. So what we're actually doing is that we want to come from here to make this compound. And as a matter of fact, you know that one of the synthetic routes here is that we must add an ethylene to this place, right? Now, the best way to add ethylene is to use Grignard, is to use organolithium reagent, which is something like this. That's the best way to add ethylene, to use the organolithium reagent. Now, the first thing we are going to do is take this structure and then try to make something meaningful from them. So let's draw the structure of O-methyl estrone. O-methyl estrone will give us something like this. Of course, at this position, you have methyl group attached, O-methyl. Then I told you that the estrone, they are usually aromatic ring. And then you have something like this. Then something like this. Then something like this. Double bond O. Something like this. Alright? Now, what is the first step we ought to take in this synthetic rod? Is to try and reduce this ring and also this one. But for me, I may not necessarily even touch this ring here. I may not necessarily touch this ring here. I'll just leave it. But if you want to read, according to the synthetic distance in the material, you have to reduce that. It's called Birch reduction. When you use liquid ammonia in ethanol, C2H5OH. What the Birch reduction will do to reduce this cyclic double bond, double bonds, instead of us to be having three of them, we are now going to be having two, and it will also reduce this group here to OH. So what are you going to get as the structure now? What I'm going to just do, I'll copy this one. Is it possible to drag? I don't have the time to start drawing this over and over again. Oh God, this is not what I wanted though. Alright, so I just bring this onto this position, and then I modify some structures from inside of here. This group will no longer be here. Then at the end of the day, you are going to, no, not to move this. You're now going to have a double bond here, double bond here. Then this group here we change to what? OH. That is reduction. Reduction can either be you are reducing the double bond or you are reducing the OH. Now, the next step is hydrolysis. Hydrolysis followed by using HCN and methanol. MEOH means methanol, which is still the same as CH3OH. Are you getting it? Now, what will hydrolysis actually do? To hydrolyze this group here to OH. To hydrolyze this group here to what? OH. And at the end of the day, the same hydrolysis will cause this bond here to leave. Now, there are various steps that actually took place here, but they actually jump most of those steps. So we'll just take it with the simple steps we are seeing here, just for you to memorize it. So we have this group here. Like I told you, what they actually did was this group here will now give us a double bond oxygen, and then this group will no longer be here. This group fall into the position it ought to be. Then we'll have OH. And then the last step is to use the the organolithium reagent. Told you what the organolithium reagent will do. It will actually attach itself to this position. Is that okay? Now, if it attaches itself to that position, I'm going to copy this. I'll bring it here. It attaches itself here. What you are going to be having, at least it should be alpha, right? So you are going to be having C, triple bond, and then you have CH. And this is the structure of sorry, let me break it down. Norethystyrene. This is the structure. So this is how you can actually get non-ethystyrene from O-methylestrone. Now, one of the most important things they actually will be marking in this thing are whether you put the appropriate reagent. 1, the appropriate structure is drawn. 2, are you getting it now? Now, this structure you see here is called non-19-testosterone. Why is it non-19-testosterone? This is structure of testosterone. Testosterone are androgens. Go east, and androgen will have 19 carbons, right? Now, if androgen have 19 carbons, it means there's supposed to be a carbon atom here to complete it 19. But you don't see that here. That is why they call it non-19-testosterone. Tell you that at position number 19 there is no group, but it's actually the structure of testosterone. Once I add one bond here, it becomes testosterone, but because it's not there, we call it 19 testosterone. Is that okay? So that is the way to synthesize this from that. Then we have the next thing. Think the next question. We've already discussed the SAR of progestin. Then outline the uses of prostaglandin analog in clinical practice. Dinoprostol is used intraamniotically. This is something that we already learned in ecology, right? It's used intraamniotically to induce labor or abortion within the first trimester, right? Then carboprost is also used to induce pregnancy. Induce labor. For it's an abortifacient, an abortifacient. Dinoprost, or they call it dinoprostol or dinoprost. Now, okay, we've done dinoprost. We are talking about carboprost. It's also an abortifacient, but it ameliorates postpartum hemorrhage. That means bleeding afterward, giving birth. It's also used to ameliorate it. The aprostradiol, supposed to be D, no E, is used to prevent closure of the ductus arteriosus in infants with congenital defect. You see in our note, I can still remember the exact word they used then. Say aprostradiol is used to maintain the patency of the ductus arteriosus in infants with congenital defects that restrict pulmonary or systemic blood flow. Then misoprostol is used as what? An ulcer protective. This one came out objective question, Ecology 2000 and Ecology, year 3. Ecology, yeah, year 3 Ecology came out as a question. Dash misoprostol is dash, whether it's an ulcer protective, what dash an ulcer protective, and then put options there. Correct answer was what? Misoprostol. I believe that is everything that this one has to do with it. So we have dinoprostol. What did I say dinoprostol is used for? It's used intraamniotically. That is through the amniotic fluid to what? Induce labor or abortion within the first trimester. Carboprost is used to treat postpartum hemorrhage. Aprostradiol is used to prevent the patency or to maintain the patency of the ductus arteriosus. To maintain. If you are preventing the closure, that means you are maintaining it because it ought to be what? Open. Then misoprostol is used as an what? Ulcer protective. All these ones, they are uses of prostaglandin analog. I think that is all for this particular one. We'll see in the next one. Bye bye.